Hello and welcome to this segment on the mechanical properties of materials. Today we'll continue our discussion that we started in the previous segment on strength and ductility of material. So the toughness, resilience, and hardness of the materials are properties that describe various aspects of how the material resists loads. So if we look at the idea of resilience and toughness is to find out how much energy would the material absorb before it gives up. So we have basically possibility that the material absorbs energy if we have an impact load, for example, and once the impact load is released, then the material recovers back its shape. So in this case, the absorption is in the elastic regime. Another possibility, if we have, say, a crash of an automotive part, the front part of the automotive design, the front part of the car is usually designed for crash resistance. And therefore, it's not so significant or important that the car bounces back to the original shape. So in the case of a crash, our idea is to absorb as much energy as possible without harming the passengers. And therefore, we would continue the deformation beyond the elastic regime all the way to plastic regime. The units of both resilience and toughness, these are two different words, is joules per meter cube. This is energy per unit volume. So if we look at the engineering stress strain curve, and the material deforms all the way to the elastic limit, then the area under the curve is an energy per unit volume. And the energy per unit volume in this case is an elastic energy that is absorbed. If I remove the load, then the material goes back to original shape, and we will define this as the resilience. So the modulus of resilience, U sub R, is the area. If I just go to the elastic limit, that would be, we can compute it. However, in most cases, the elastic limit is very close to the yield point, and in tables and properties, we do not have access to the elastic limit, but we have access to the yield point very easily. So as an approximation, we will approximate the area of this heavily shaded triangle here with the area all the way up to the yield point, including the difference between the elastic limit and the yield strength of material. So this will be approximately half of the base of the triangle times the height, so half epsilon yield times S yield. And for all practical purposes, the yield strength is proportional to the yield strain if we ignore just the small deformation here beyond the elastic limit. So this will be approximately equal to 1/2 S yield over E times S yield, and therefore I can now write it as the U sub R is approximately equal to S yield divided by 2 S yield squared divided by 2E. So this is like a formula that I can use to determine the modulus of resilience of the material. Here is a summary. The accurate way to calculate is by an integral from 0 to epsilon yield, and the area, the integral can be replaced by the area of the triangle, and the area of the triangle now I use the linear relationship to eliminate the epsilon yield because we don't need it, in lieu of the yield strength of the material, S yield. So next index that describes the material's resistance to crash is toughness. And toughness, as I mentioned, we design it to go all the way to plastic regime. So again, the energy per unit volume is the area under the curve. So U sub T, the modulus of toughness, is the area under the curve, and we can define it. U sub T is the integral from 0 to epsilon F. Epsilon F is the failure strain of the material of sigma d epsilon, regardless. So we're going to have part of it is going to be elastic and the other part is plastic. If we know our relationship between sigma and epsilon, for example, if we use the Ramberg-Osgood relationship, we will be able to compute that modulus of toughness U sub T. Because the relationship between sigma as a function of epsilon is sometimes difficult. I mentioned Ramberg-Osgood, but if you want to do a quick approximation, we can have a much easier way to do it by a simple approximation. And the approximation is to take like an average value of the stress between the ultimate and the yield. So this average value is S yield plus S ultimate over 2. So if I take that average value, then I can compensate for the area above the average and calculate the area of this rectangle. And the area of this rectangle would be approximately equal to the modulus of toughness. And therefore the modulus of toughness is the base of the rectangle, epsilon F, times the value of this height, and the height is the average between the yield strength of the material and the ultimate strength of the material. So with this, we've reached the end of this segment on our discussion of the resilience and the toughness of materials and their applications. And with this, we'll finish our video. Thank you for watching, and we'll see you on our next video.